Okay, so we already showed that all the partitions, for all partitions and the bounded functions, lower sum is less than or equal to the upper sum for the same partition. And we also showed that for the refinement of the partition, lower sum is increasing, upper sum is decreasing. Refinement. Now we are going to prove that for arbitrary two partitions, if P and Q are any partitions, of course over the same interval. Okay, any partitions of the same interval, then the lower sum is always less than or equal to the upper sum. So this one is a strong result than the remark 5.6. Remark 5.6 here is also P. Okay. Well. Okay, so we're going to prove that. The important, well, this proof is very simple. It's a direct application of 5.7. The 5.7, just keep in mind for refinement, lower sums are increasing, upper sums are decreasing. Okay, so this is a 5.7. But this place, there's no refinement. There's no refinement. Let me. Okay, there's no refinement. How do we get a refinement? Remember, we have the remark. P union Q is a refinement of P and Q. So even P and Q have no relation, but P union Q is related to P and Q. So P union Q is a refinement of P and Q. So by the lower sum relation, it's increasing. You have a refinement, you increase the lower sum. And this is a 5.7. And the lower sum is less than or equal to the upper sum for the same partition. This is 5.6. And then we back to the 5.7. Upper sum is decreasing, so you have a refinement, then this is a 5.7. So you see here, with this bridge, we get the lower sum of P is always less than or equal to the upper sum of Q. Okay, so that's a combination of a the refinement remark 5.6 and the 5.7. Okay, so you get a partition, you refine it, then you will have a decreasing U. And because it is bounded below, you see here, the upper sum is always bounded below for all upper Riemann sum. They are bounded below. With respect to the refinements. Okay, with respect to the refinement, it's bounded below. Okay, and for all lower sum they are bounded above with respect to the refinement. You have refinement better and better, and then it's bounded above. Bounded below it has an infimum, finite infimum. Bounded above it has a finite supremum. Okay, so they approach this point, the upper sum approaches this point, lower sum approaches this point. So this is lower sum, this is upper sum. When they approach to certain number, this number we will call it the integral. Okay, for this number we will call it the integral of the function over the interval. Okay, and when they approach to this number, here you have a lower sum, here you have an upper sum. The difference will be extremely small, or smaller than any given number. So that's the idea of the following definition. Okay, the definition is the following. Let A be being R with A less than B, a function f from AB to R is said to be integrable or Riemann integrable. On the interval AB if and only if f is bounded. So this is definition, it's not the state theorem, so it's a condition. So bounded by definition, it means, so first you have to have a bounded function, then you can define the upper sum and lower sum. It's bounded on AB, and for every epsilon greater than 0, there is a partition P of AB such that the upper sum minus the lower sum is less than epsilon. They're very, very close to each other. So the limit is there. So the integral will be there. Okay. Okay. So this is the definition, the integral stuff. Okay. So in this definition, we define the integrability. We just say it is integrable. But we don't say some number is integral. Okay, just integrability. Okay, so let's check. So first, we know that in the Riemann stuff, in the calculus, we know all the continuous function will be integrable over the closed interval. Now let's use the solid proof to show that. Remember, continuous function over closed interval is always bounded, so it satisfies the condition function should be bounded. And we're going to show that continuous function also integrable in this sense. In this sense, it will be integrable. So suppose that AB in R with A less than B. If f is continuous on the interval AB, then f is integrable on AB. F is going to be integrable on AB. Okay, so we're going to prove based on this definition. So proof. We know that function is continuous over closed interval, then function is uniformly continuous. So remember here is epsilon, so given epsilon greater than 0. F is continuous over AB, then F is uniformly continuous. Uniformly continuous. Uniform continuity means there is a delta greater than 0 such that x minus y less than delta implies fx minus fy is going to be less than epsilon, right? That's a uniform continuity. Because in the future we want to make this looks better, and actually we're going to multiply this epsilon with some coefficient, then that coefficient should be make the final computation epsilon. Let make this part exactly epsilon, not with certain coefficient. So in the book they use epsilon over b minus a, epsilon over b minus a. You consider it's a 1 over b minus a times epsilon. You will see why they put this coefficient later. Okay. Well, let's see why. Okay, so well, let p x0, x1, xn be a partition of AB, just arbitrary partition, be a partition of A and B, with, of course, we want it very good, so the length of subintervals is less than delta for all subintervals. Okay, and for the j's subinterval, there are by the extreme value theorem, theorems, there are x little m and x capital M in xj minus 1 xj, with mjf is fx little m, capital MJF is equal to f x capital M. So you can really get the supremum and the maximum over the j's subinterval, okay, and x little m, x capital M, both inside xj minus 1 xj, x capital M minus x little m, the difference is less than delta. Where's delta? Here, the norm of the partition is less than delta, right? So what? So the ops value fx capital M minus fx little m, this is a maximum, this is a minimum. It is mjf minus little mjf, and this is less than epsilon over b minus a. less than epsilon over b minus a. For every pair, if the distance is less than delta, then the distance of values will be less than epsilon over b minus a. Okay. Okay, so that's the difference of maximum and the minimum. Now let's check the upper sum and the lower sum. Upper sum and lower sum, remember, you can write it as capital MJF minus little mjf. Remember, this is past non-negative times xj minus 1. This is also non-negative. Each of them may be negative. U and L, they might be negative, but the difference is always non-negative. It's always non-negative. Okay, then this one is less than epsilon over b minus a, and times a positive number is also. No, we don't need equal sign. Here there's no equal sign. Epsilon over b minus a, xj minus 1. This is constant. You move it forward, then you're going to add xj minus 1. That is total length of the interval. This is epsilon. So here over b minus a is exactly to cancel this b minus a. Okay, so this is the proof why a continuous function is integrable. For every epsilon, you can always find a partition so that the upper sum minus lower sum is less than the given epsilon. It's less than the given epsilon. Okay, so this is a integrable function. All the continuous functions will be integrable. All the continuous functions will be integrable. Okay, next, let's show that the Dirichlet function is not Riemann integrable. Okay, so first let's recall what is a Dirichlet function. The Dirichlet function is fx equal to 1 if x is a rational function, 0, a rational number, 0 if x is not a rational number. Okay, then we show that fx is not Riemann integrable. On 0, 1. It's not Riemann integrable on 0, 1. How? Okay, so Riemann integrable means for epsilon you have something. Not Riemann integrable. Well, let's see. Let P x0, x1, xn be a partition. Partition of 0, 1. Then for subinterval xj minus 1, xj, the maximum interval always contains rational number, irrational number. At a rational number is a 1, irrational number is 0. So the supremum is always a 1, and the infimum is always 0. Supremum is 1 and the infimum is 0, right? And then the upper sum minus a lower sum. Upper sum is sigma j from 1 to n, 1 times xj minus 1. Lower sum is j from 1 to n, 0 times xj minus 1. Well, 0 times, this lower sum is constantly 0. Upper sum is a 1. 1 you don't have to copy. This is telescope sum. So this is exactly 1. So the difference is constant for arbitrary arbitrary partition, so you can never find a partition so that the difference is less than epsilon. 1 epsilon is less than 1. So f is not integrable over 0, 1. So integrable just means, like what I draw here, the lower sum and upper sum, they will approach to the same point, but here the difference is always 1, so they will not approach to the same point, right? Okay, so that's it. And of course, you can see that the constant function is always integrable, right? The constant function, the upper sum, lower sum, they equal to each other, so the difference is 0. And now let's see if there's a break. What do I mean? The break, fx. fx is 0 and 1. 0, 1, x is between 0 and 1 half, excluding 1 half. 1 if x is including 1 half and 2, 1. Okay, so this is a break, a step function. Okay, this function. And we're going to show this function is integrable on 0, 1. This function is integrable on 0, 1. Okay, so how do we show it? Let a proof given epsilon greater than 0. Given epsilon greater than 0. Okay, so the problem, you see, the upper sum, lower sum identical over this part. Upper sum, lower sum identical over this interval. The only problem happens at 1 half. At 1 half, you have trouble. So we're going to construct a partition. We have 0, epsilon, 1 minus epsilon over 1 half, and 1 plus epsilon over 1 half, and 1. So basically, you just choose a small interval here. 1 half to the left, half epsilon, to the right, half epsilon. Okay? And of course, here, epsilon should not be very big. If epsilon is greater than 1 half, then you will exceed, right? So we assume that epsilon is less than 1 half. If epsilon is too big, you don't worry about it. We always worry when epsilon is small. Okay, and let's see the UFP minus LFP. So we have 3 intervals, 1, 2, 3. Over the first interval, it's a constant function. Over the third interval, it's a constant function. Only over the middle interval. So it's from 1 plus epsilon over 2 minus 1 minus epsilon over 2. This is interval. And the supremum is 1, infimum is 0. So the difference is 1. So this is exactly epsilon. Okay, it's exactly epsilon. So epsilon less than or equal, or in the definition you can just put less than or equal to, it doesn't matter. So for every epsilon you can find a partition so that the difference is less than epsilon or less than or equal to epsilon. So f is integral. F is integral. Okay, so that's the proof. Okay, cool. So again, what is the integrability? Integrability just means they approach to each other. The upper sum, lower sum, they will approach to each other. That number will be called the integral. What is that number? That number is actually the infimum of the upper sum, supremum of the lower sum. So definition, let A be in R with A less than B, and F from AB to R be bounded. Then first, the upper integral of f on AB is the number they put up integral from A to B. We just write it by this. This is a number. It's by definition the infimum of all the upper sums. Infimum means the function does not change, so the partition changes. The partition changes. This is upper sum. Upper sum is the infimum of the upper integral is the infimum of the upper sum. The lower integral of f on AB is the number. The lower integral is the supremum of the lower sum. Is the lower sum. Upper integral is infimum, lower integral is the supremum. And if the lower integral is equal to the upper integral, then we define the integral of f on AB to be those numbers. Of course, it's also equal to the lower integral. Okay, this is quantity. This is quantity. The previous definition is property. Is integrable or not integrable? And this definition is a quantity, what quantity we have. Okay. Okay, so that's integrability. And when we talk about the integrability, we always say A is less than B. If A is equal to B, to be the convention when we try to interpret the integral, interpret the area, integral as an area, we separately define when A is equal to B. We define it to be 0 for all bounded functions. For all bounded functions. Again, this definition works for bounded functions. Okay? This definition only works for bounded function. If you do not have bounded function, you don't talk about this. Okay. We know that this function, this is bounded, not this one. The Dirichlet function is bounded function. So bounded functions may not be integrable. in this sense. But we know that the upper and the lower integrals always exist. Upper and the lower integrals always exist. It's just because all the upper sums are bounded below, all the lower sums are bounded above, right? Upper and lower integrals always exist. And also, even though they may be different, but they have a weak relation. The lower integral is always less than or equal to the upper integral. This is the relation. Even though they may be different, but they're always less than or equal to the lower integral is always less than or equal to the upper integral. The proof is simple. The proof is a core application of this result 5.8, the remark we discussed at the beginning of the video. Okay, so a lower sum is always less than or equal to upper sum for whatever partitions P and Q's. Okay, P and Q are not related, they're independent. And then we say this number is the lower sum of the whole upper sums. The lower sum is a lower bound. So LFP is a lower bound of all upper sums. Then it will be less than or equal to the infimum. The infimum is the upper integral. The infimum of all upper sums is upper integral. Okay, so first you choose the infimum of the right hand side, you get a fixed number. Now this is a fixed number. So this fixed number is an upper bound of all lower sums. It's upper bound, then the supremum will be the smallest upper bound. See the logic behind those arguments. Okay. Okay. So that's the remark. Even though not all bounded functions are integrable, but they do have the lower bound and upper bound. They do have the lower bound and upper bound. Okay. Well, we have integrability and we have integral. We have integrability and we have integral. Then the theorem 5.15 will unify them. Okay. So let A be in R with A less than B, and F from AB to R be bounded. Okay, we have bounded function. Then F is integrable on AB, integrable if and only if the lower integral is equal to the upper integral. Okay, the lower integral is equal to the upper integral. This is an if and only if case. Actually, we define two definitions and they are equivalent. They mean the same thing. But one is about the property, the other one about the quantity. Okay, so there's two directions, two proofs. Part 1. F is integrable. F is integrable. That means given epsilon greater than 0, there exists a partition P such that what? Such that the what? The upper sum minus the lower sum less than epsilon. Okay, upper sum minus lower sum is less than epsilon. Well, let's list some order. So L, F, P, the lower sum. Lower sum is of course less than or equal to the supremum, right? This is supremum. It's greater than. This is smallest upper bound. Okay, and for the supremum, the lower integral, by the previous computation, we know that lower integral is always less than or equal to the upper integral, right? And the upper integral is the infimum is always less than or equal to whatever upper sum. So that's an order. That is the order. And now we know this is a positive. This is a positive. And we know that this point minus this point. So the upper integral minus the lower integral is going to be less than or equal to upper sum minus the lower sum and less than epsilon. While this is a fixed number, the difference of the lower sum, upper sum, they change, but this is a fixed number. The fixed number is greater than or equal to 0 and less than epsilon, whatever past the epsilon. Hence, the upper integral minus lower integral is equal to 0. And that's it. Equal to 0, the equal to chapter. So you prove that if it's integrable, then you have integral. It sounds tautological, but if it is integrable, the integral exists. Right? If it is integrable, then the integral exists. Right? And the other way, if the upper integral is equal to the lower integral, if the upper integral is equal to the lower integral, first, given epsilon greater than 0, given epsilon greater than 0, given epsilon greater than 0, this is a supremum. Supremum has, this is infimum. There is a partition P of AB with, this is infimum. Remember, this is infimum. Infimum means whenever you add a tiny stuff, then you will have a point between the infimum and this number. That's infimum. And for the same thing, there's a partition. This, let's use P1. There is a partition P2 of AB with, okay, now L is a supremum. Supremum, subtract supremum. Subtract from supremum. There is a LFP2 less than or equal to, right? Okay, so you have two partitions and they satisfy those properties. But we need one. Which one? Naturally, the union of them. Let P be P1 union P2. Let P be P1 union P2. Right? With this one, remember the lower sum is increasing, upper sum is decreasing. So actually, when you have this P, you're going to add a lower sum LFP here. And you will get upper sum decreasing, UFP here. Right? Lower sum is increasing, it's close to the supremum. Upper sum is decreasing, it's close to the infimum. So what do you have? You have, let's rewrite it. Upper. Let's do lesser. And the other one is I remember these two numbers are the same. These two numbers are the same. Actually you can get the chain of them. You get the chain of them. Get chain of them. These two end numbers, the difference is epsilon. Yes. It's less than epsilon, and that is integrability, right? That is integrability. Okay, and that's it. That is the proof about the equivalence of these two statements. The equivalence of these two statements. Okay. Okay, so let's see another convention. In this whole proof, we always assume A is less than B. What happens if A is greater than B? So if A is greater than B, we define to be negative integral from to match the property of the regular Riemann integral. And this is actually also makes sense. It also makes sense. Because in the definition, you still use xj minus 1. If you get the opposite direction, you will have a negative sign. Okay. Okay, so by the integrability, we know the constant function is integrable. And actually, if we just try to compute the integral, we also have the lower sum, upper sum, they are constantly alpha b minus a. So the integral of the constant function is always alpha b minus a. So constant function is always integrable in whatever sense you just defined. All right. So this is the integrability, the first part, the first section. Remember that the integrability has two important concepts. One is integrable. The other one is integral. Integral is a quantity. Integrability is a property. And they equivalent. Integrability will imply the existence of the integral. The existence of the integral will imply the integrability. So later, it doesn't matter what number or what concept you talk about. It is always correct. Okay? Okay, so we finish this section and we will continue the next section in the next video. Thank you very much.